Alright, so today in this comprehensive video, we're going to cover diffraction, which is an essential topic for your exam. We'll explore single-slit diffraction, double-slit diffraction, diffraction gratings, and much more. By the end of this video, you'll have a solid understanding of the mathematical expressions and key concepts related to diffraction along with its applications. So let's get started. When light passes through a single slit, it spreads out and creates a diffraction pattern of bright and dark fringes on a screen. This pattern is the result of the wave nature of light, where the light waves interfere with each other. The central bright fringe is the most intense, with secondary fringes of decreasing intensity on either side. The position of the dark fringes, or minima, in this pattern can be determined using this equation. Here, A is the slit width, theta is the angle of diffraction, lambda is the wavelength of light, and m is the order of the minima, where m is equal to plus or minus 1, plus or minus 2, so on and so forth. The intensity distribution of light varies with the angle, with the central maximum being the brightest. As you move away from the center, the intensity decreases, and the dark fringes represent points of destructive interference. In the double-slit diffraction setup, light passes through two closely spaced slits, creating an interference pattern of bright and dark fringes on the screen. This pattern arises from the superposition of light waves coming from the two slits, demonstrating the wave nature of light. The classic experiment demonstrating this phenomenon is Young's double-slit experiment. The condition for constructive interference, where bright fringes, maxima, occur, is given by the equation, which is d sine of theta is equal to m times lambda. In this equation, d is the distance between the slits, theta is the angle of the fringe, lambda is the wavelength of light, and m is the order of the maxima, where again m is equal to 0, plus or minus 1, plus or minus 2, so on and so forth. The alternating bright and dark fringes result from constructive and destructive interference. The alternating bright and dark fringes result from constructive and destructive interference, respectively. Understanding this pattern is crucial for interpreting the wave behavior of light. A diffraction grating consists of many closely spaced slits, which produce a diffraction pattern with sharper and more defined maxima compared to a double-slit setup. The condition for maxima is similar to that of the double-slit experiment, which again is the equation d sine of theta is equal to m times lambda. Here, d is the spacing between the adjacent slits in the grating. The multiple slits cause the light to interfere in such a way that the maxima are much sharper, making diffraction gratings ideal for applications where precise wavelength measurements are needed. Diffraction gratings are commonly used as spectrometers to resolve the wavelength of light into its components, allowing for detailed spectral analysis. The resolution of an optical system refers to its ability to distinguish between two closely spaced objects. Diffraction limits this ability, as light waves spread out when passing through an aperture. The Rayleigh criterion provides the minimum resolvable angle theta given by theta, which is equal to 1.22 times lambda all over d. Here, lambda is the wavelength of light, and d is the diameter of the aperture. This criterion is essential in understanding the limits of resolution in optical instruments like microscopes and telescopes. When two point sources are closer than the Rayleigh criterion allows, they will appear as a single point, highlighting the importance of aperture size in resolving detail. Interference patterns result from the superposition of light waves, leading to regions of constructive interference, or bright fringes, where waves are in phase, and destructive interference, or dark fringes, where waves are out of phase. In diffraction and diffraction patterns, the bright fringes correspond to constructive interference, while the dark fringes correspond to destructive interference. This principle underlies many optical phenomena and is crucial for understanding diffraction. Diffraction has several important applications in science and technology. The first is X-ray diffraction. This technique is used to study the crystal structure of materials. When X-rays pass through a crystal, they are diffracted in specific patterns that reveal the arrangement of atoms within the crystal. Second is electron diffraction. Demonstrating the wave nature of particles, electron diffraction is used to study the structure of materials at the atomic level, similar to X-ray diffraction, but with electrons. These applications highlight the versatility of diffraction as a tool for probing the structure of matter at very small scales. When light passes through a circular aperture, it creates a diffraction pattern known as an airy disk. This pattern consists of a central bright spot surrounded by concentric rings of decreasing intensity. The airy disk is particularly relevant in optical instruments like telescopes and microscopes, where it limits the ability to distinguish between closely spaced objects. Understanding the airy disk is crucial for designing and using optical systems that require high resolution. Now, let's consider the types of passages you might encounter on your exam based on these topics. You could see a passage discussing single-slit diffraction, where you'll need to calculate the positions of dark fringes using the diffraction formula. Another passage might describe Young's double-slit experiment, requiring you to analyze the interference pattern and calculate the wavelength of light based on the positions of the bright fringes. You might also encounter passages involving X-ray diffraction, where you'll need to interpret diffraction patterns to determine the structure of a crystal. Understanding how diffraction patterns relate to atomic spacing will be key here. Now, let's challenge your understanding with a couple of practice questions. These questions are designed to test your grasp of diffraction concepts. Question 1. In a single-slit diffraction experiment, the slit width is 0.5 millimeters, and the wavelength of light is 600 nanometers. What is the angle theta for the first minimum? Please pause for a moment and take your time. Now, using the equation, A sine of theta is equal to m times lambda, with A being 0.5 millimeters, lambda being 600 nanometers, and m being 1. Sine of theta is equal to 1 times 600 times 10 to the negative 9th meters, all over 0.5 times 10 to the negative 3 meters, which gives us theta sine, or inverse sine, of 600 times 10 to the negative 9th over 0.5 times 10 to the negative 3, which is about 0.069. So to excel in your exam, it's crucial to master the following key points. Understanding how light passes through a single slit creates a diffraction pattern, and how to calculate the positions of minima using A sine theta is equal to m times lambda. Be familiar with the double-slit diffraction pattern and the mathematical expression for maxima, d sine of theta is equal to m times lambda. Recognize the sharper maxima produced by diffraction gratings and their application in spectrometry, and learn the Rayleigh criterion for the limits of resolution and its significance in optical instruments. And finally, knowing the applications of diffraction, such as X-ray and electron diffraction, and the formation of airy disks through circular apertures. So in summary, understanding diffraction is essential for mastering concepts in wave optics. By grasping these principles, you'll be well prepared for your exam and future studies. And if you found this video helpful, don't forget to like, comment, and subscribe to our channel for more educational content. And if you're in the app, please like the video there. Your support helps us continue to create informative videos to aid your study journey. Good luck studying.